Hello, in this lecture we'll answer two questions. In the first question, we'll find out the size of this angle APC is equals to x, so we have to find out the value of this angle x. And in the second question, we'll find out the length of line segment CD is equal to x. So we have to find out the length of line segment x is equal to CD. So we start with the first question. In the domain, we have triangle ABC. This is angle ABC. This equals to 30 degrees in size. This is angle this is angle ABC. This equals to 15 degrees in size, and this is angle ACB. This equals to 30 degrees in size. In addition, we know that BP equals to PC. So if we define the length of side BP as A, then the length of side PC must be equal to A because they are equal to each other according to what is given as a question. Again, our task is to find out the size of this angle APC. This equals to x. So we have to find out the value of this angle x. So first of all, we will do a construction. That is to say, we will extend side CA of this side ABC by a straight line. And then we create angle of 15 degrees at point B in such a way that BA will be one leg of this angle of 15 degrees, and the other leg that we construct, we create 90 degrees from the leg BA. Okay? The other leg that we construct at point B will be, we create 15 degrees, and this leg BA. So this is angle AB. Is equals to 15 degrees in size according to our construction. In the next step, we will extend this leg by a straight line until it touches the extended side CA. And we define the touching point of the extended side CA with this extended leg. This point is point M. By doing this construction, we created the associated triangle BMC. Why triangle BMC is an associated triangle? Because of the fact that those two angles are both equal to 30 degrees and therefore they are equal to each other. BC is the base of the associated triangle BMC. Repeat again. Side BC is the base of this associated triangle BMC. So I did now triangle BMC is an associated triangle. And BC is the base of this associated triangle BMC. So here we can implement rule 20. I repeat quickly on rule 20 that talks about an associated triangle. According to rule 20, the perpendicular to the base of an associated triangle bisect the base. In the drawing, we have the associated triangle ABC. Triangle ABC is an associated triangle because of the fact that those two sides are equal to each other. And according to this rule 20, here the base BC is the base of this associated triangle, triangle ABC. According to this rule 20, the perpendicular to the base of an associated triangle, that is to say AD is perpendicular to the base BC. That is to say this angle equals to 90 degrees and this angle equals to 90 degrees according to a construction. According to this rule 20, the perpendicular AD to the base BC bisects the base BC. So at point D, the base BC has been bisected into two halves. The first half is BD, and it of course equals to the second half DC. Each half equals to BC over 2 because of the fact that BC has been bisected. So in total, in this triangle in BD, according to rule 20, the perpendicular AD to the base BC bisects the base BC. That is to say, the first half of BC is BD, the second half is BDC. And of course, the first half BD equals to the second half DC, and each half equals to BC over 2 because of the fact that BC has been bisected by the perpendicular AD. So we can implement rule 20 in our drawing. In our drawing, this is the associated triangle BMC. The base of this associated triangle BMC is BC. According to rule 20, the perpendicular from point M to the base BC bisects the base BC. Well, the perpendicular from point M will touch the base BC. The perpendicular from point M to the base BC must touch the base BC at point P. Why? Because of the fact that point P is the midpoint of the base BC. Why point P is the midpoint of the base BC? Because of the fact that at point P, the base BC is being bisected. The first half of the base BC is BP, that is equals to A, and the second half of the base BC is PC, that is also equals to A. Therefore, the perpendicular from point M to the base BC will touch the base BC at point P and not in any other point. So, MP is a perpendicular to the base BC, that is to say, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. According to rule 20, the perpendicular MP to the base BC bisects the base BC. That is to say, the first half of the base BC is BP, that is equals to A, the second half of the base BC is PC, is also equals to A, and each half equals to BC over 2 because of the fact that BC has been bisected. The next step will focus on this right triangle BMP. And we define the hypotenuse MB as 2B. Again, MB equals to 2B according to our definition. MB or BM is equal to 2B units in its length according to our definition. So in this right triangle BMP, sin 30 degrees equals to MP over MB. Again, sin 30 degrees in this right triangle BMP equals to MP over MB. So until now, this right triangle BMP sin 30 degrees equals to MP over the hypotenuse MB. But again, in the right triangle BMP, it is very easy to see that sin 30 degrees equals to MP over MB. So it is equals to MP over MB. MB equals to 2B units in itself according to our definition. So we substitute MB by 2B. Those two sides of the equation are equal to each other. That is to say, sin 30 degrees equals to MP over 2b. Sin square 30 degrees equals to 1 half. So we substitute sin square 30 degrees by 1 half. So 1 half equals to mp over 2b. Here we will multiply this equation by 2b, and we get that here in the side of the equation we have 2b over 2 equals to mp. We have 2 in the denominator of this expression, so 2 will get cancelled. After I cancel 2, we found out actually that mp equals 2b. So actually, this is the perpendicular mp to the base bc, and it equals to b units in its length. So in conclusion, we shall find out that if bm equals to 2b, then mp will be equal to b. So this is the big associated triangle BMC. This big associated triangle BMC, AB is the angle bisector of angle MBA. Again, AB is the angle bisector of angle MBA. Angle MBA equals to, in total, to 30 degrees, and angle bisector AB bisect angle MBC into 2 halves. The first half is 15 degrees, and the second half is 15 degrees. So in the big associated triangle MBC, AB is the angle bisector of angle MBC. And therefore, we can implement here rule 19. Rule 19 is also defined as angle bisector theorem. So please click here on rule 19. This is triangle ABC. That could be any triangle. AD is the angle bisector of angle BAC triangle ABC. Again, AD is the angle bisector of angle BAC in this triangle ABC. That is to say, AD bisects angle BAC into 2 halves. Each half equals to theta. And because of the fact that AD is the angle bisector of angle BAC in triangle ABC, then angle bisector AD divides the size of this triangle ABC proportionally. That is to say, BD over BC equals to AB over AC. Again, because of the fact that AD is the angle bisector AD divides the size of this triangle ABC proportionally. That is to say, BD over DC equals to BA over AC. Again, BD over DC equals to BA over CA. So we can implement angle bisector theorem. This is also defined as rule 19 in our associated triangle BMC. So in the associated triangle BMC, AD is the angle bisector of angle MBC in the associated triangle MBC. And because of the fact that AB is the angle bisector of angle MBC in the big associated triangle MBC, according to rule 19, that is also defined as angle bisector theorem, angle bisector AB divides the size of the big associated triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. Again, according to angle bisector theorem, because of the fact that AB is the angle bisector of angle MBC in the big associated triangle MBC, angle bisector AB divides the size of this big triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. So write it down. So in the big associated triangle MBC, line segment AB is angle bisector or angle MBC. Angle bisector MB is angle bisector of the big angle and angle MBC. Therefore, according to angle bisector theorem, angle bisector AB divides the size of this big triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. Okay, again, because of the fact that AB is the angle bisector of angle MBC in the big triangle MBC, angle bisector AB divides the size of this big triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. According to Rule 19, it is also defined as angle bisector theorem. We already found out that MB equals to 2B according to our definition, so we substitute MB this equation by 2B. Over BC. BC in total equals to BP, that is A, plus PC, that is A. So BC in total equals to A plus A, that is 2A. So we substitute BC in this equation by 2A. So in total this is the equation MB over BC equals to 2B over 2A. And it's equals to MA over AC. So in total we found out that according to angle bisector theorem, it is also defined as Rule 19, 2B over 2A equals to MA over AC. We have 2 denominator, 2 in the denominator, so 2 will get cancelled. So in this is the equation we have to leave B over A equals to MA over AC. So in total we found out that B over A equals to MA over AC. In the next step, we'll focus on this right triangle MPC. This right triangle MPC this is line segment AP, line segment AP divides of this the size of this right triangle MPC proportionally. Repeat again. This right triangle MPC, right side AP divides the size of this right triangle MPC proportionally. In the right triangle MPC, right side AP divides the size of the triangle MPC proportionally. That is to say, B over A equals to MA over AC. And again, we already found out that B over A equals to MA over AC. And because of the fact that the size of this right triangle MPC divided proportionally by line segment AP, line segment AP is defined as the angle bisector for angle MPC in the right triangle MPC. And therefore, line segment AP is defined as angle bisector of line segment AP is defined as angle bisector of angle MPC in the right triangle, triangle MPC. This is according to Rule 21. Repeat quickly on Rule 21. This is triangle ABC that could be any triangle. This is line segment AD. Line segment AD divides the sides of this triangle ABC proportionally. That is to say, we know that BD over DC equals to AB over AC. Again, BD over DC equals to AB over AC. BD over DC equals to AB over AC. And because of the fact that line segment AD divides the sides of this triangle ABC proportionally, line segment AD is defined as angle bisector of angle BAC in this triangle ABC. Line segment AD is defined as angle bisector of angle BAC in this triangle ABC. That is to say, line segment DA divides angle BAC into two halves, each half equals to theta. So actually, it is the converse rule of angle bisector theorem. Rule 21 is the converse rule of Rule 19. Well, according to Rule 19, if we know that AD is angle bisector of angle BAC in this triangle ABC, then angle bisector AD divides the sides of this triangle, triangle ABC proportionally. That is to say, because of the fact that AD is angle bisector of this triangle ABC, the following equation is to BD over DC equals to AB over AC. So the converse rule of Rule 19 is Rule 21. In Rule 21, we don't know that AD is angle bisector. This is line segment AD, but because of the fact that line segment AD divides the sides of this triangle ABC proportionally, that is to say, we know that this triangle ABC, BD over DC equals to AB over AC. And therefore, line segment AD is defined as angle bisector of triangle ABC. That is to say, line segment AD divides angle BAC into two halves, each half equals to theta. So, Rule 19 or Rule 21 is the converse rule of Rule 19. So, according to Rule 21, because of the fact that line segment AP divides the sides of this triangle MPC proportionally, that is to say, we know that B over A equals to MA over AC. Therefore, according to Rule 21, line segment AP is defined as angle bisector of angle MPC in the right triangle MPC. So, therefore, line segment AP is angle bisector of this angle MPC in the right triangle, triangle MPC. And again, this is Rule 21. This is the converse rule of Rule 19. So according to Rule 21, line segment AP is angle bisector of angle MPC. Angle MPC equals to 90 degrees in its size, and according to Rule 21, AP is the angle bisector of angle MPC. So, therefore, angle bisector AP divides angle MPC into two halves. The first half is angle MPA, this is the first half of 90 degrees is 45 degrees. And the second half of 90 degrees is angle X, that is 45 degrees in its size. So in total, we actually found out that the size of this angle X, that is also defined as angle APC, is equal to 45 degrees in its size. So in total, we found out that the size of the angle that we are looking for, the document angle APC, this is also defined as angle X, equal to 45 degrees in its side. So this is the answer to the first question. In the next step, I'll present you the second question of this lecture and an answer on the second question. The second question, our task is to find out the length of line segment CD is equal to X. Or we can say that our task is to find out the length of line segment X is equal to CD. So in the drawing we have a semicircle. Point O is the center of this semicircle. Those two angles are both right angles. In addition, we know that CQ equals to PQ equals to QE. Those three line segments are equal to each other in their lengths. So if we define the length of CQ as A, then the length of line segment QE and line segment PQ must be also equal to A, because of the fact that all those three line segments are equal to each other in their lengths according to what is given in the question. So CQ equals to PQ equals to QE equals to A. In addition, we know that this is line segment OE. This is equals to 5 units in itself. This is line segment EB. This is equals to 4 units in itself. Again, our test is to find out the length of this line segment CD. This is equals to X. We can say also that our test is to find out the length of line segment X is equals to CD. So first of all, we will join point C and P together by set 9. By joining point C and P, we created the right triangle CPQ. We have the rule that says that in front of equal sides in the triangle there are equal angles. Again, we have the rule that says that in front of equal sides in the triangle there are equal angles. So in the right triangle CPQ, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, according to the rule that I mentioned. We also know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in triangle CPQ must be equal to 180 degrees. So each angle we have this right triangle CPQ, we have alpha plus alpha is 2 alpha plus 9 degrees equals to 180 degrees. So write it down. this right angle CPQ, the sum of the areas must be equal to 180 degrees. That is to say, 2 alpha plus 90 degrees. In total, the sum of those three angles must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. 2 alpha equals to 90 degrees. Here we divide this equation by 2 and finally get that the missing angle alpha is equal to 90 degrees over 2 is 45 degrees. So she found out that those two angles are both equal to alpha, therefore each of them is equal to 45 degrees in its size. So write it down. Actually, angle CPQ, this angle CPQ is a right angle and also a isosceles angle. Why? Because side CQ equals to side CP, and therefore it is also an isosceles angle. And we can say in general that if we have a right angle that is also an isosceles angle, the angles of the isosceles angle that is also a right angle will be always 90 degrees, 45 degrees, and 45 degrees. It is true in any right angle that is also an isosceles angle. So in the next step, we join points P and D together by a straight line. Those 2 points. It is given as a question that CE is a straight line. Again, CE is a straight line according to what is given as a question. So if you focus on the upper side of this straight line CE at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 said that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line CE at point Q? We have this angle that is a right angle, plus this missing angle. In total, the sum of those angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So actually, by joining points P and D together by a straight line, we created the right angle PQE. The right angle PQE is also an isosceles triangle because of the fact that those two sides are equal to each other. Each side equals to n, therefore they are equal to each other. So, therefore, the right angle PQE is also an isosceles triangle. And you know that a right angle that is also an isosceles triangle, so we have 3 angles, 90 degrees, 45 degrees, and 45 degrees. It is true in any isosceles triangle that is also a right angle. So this angle must be equal to 45 degrees in size. And this angle must be also equal to 45 degrees in its size. In the next step, we will complete this semicircle to a circle. Completed the semicircle to a circle. So we will extend side PE by straight line until it touches the circle. Repeat again, we will extend this side PE by straight line until it touches the circle. And we will define the touching point of the extended side PE with this circle. This point is point N. Likewise, we'll extend side CE by straight line, this side CE by straight line until it touches the circle. And we'll define the touching point of the extended side CE with this circle. This point is point M. In the next step, we'll join points M and N together by straight line. Likewise, we join points C and N together by straight line. This is angle CPN. Angle CPN equals to 45 degrees plus 45 degrees. It is 90 degrees. So angle CPN is a right angle. Peripheral angle CPN, that is the right angle, subtend on chord CN. Again, peripheral angle CPN, that is the right angle, subtend on this chord CN. So here we can implement rule 5 in our drawing. So repeat quickly on rule 5. According to rule 5, any peripheral angle is equal to 90 degrees inside must subtend on the diameter of the circle. In the drawing we have a circle. This is peripheral angle MAN. We know that peripheral angle MAN equals to 90 degrees inside. Therefore, according to this rule 5, peripheral angle MAN must subtend on the diameter of the circle. Peripheral angle MAN subtend on chord MN. Therefore, according to this rule 5, peripheral chord MN must be the diameter of the circle. So according to rule 5, any peripheral angle that is equal to 90 degrees inside, like this peripheral angle, must subtend on the diameter of the circle. Mn is the diameter of the circle according to this rule 5. So we can actually implement rule 5 in our drawing. Well, because of the fact that we know that this is peripheral angle CPN, equal to 90 degrees inside. Therefore, according to rule 5, peripheral angle CPN, that is the right angle, must subtend on the diameter of this circle. Peripheral angle CPN subtend on chord CN. Therefore, according to rule 5, chord CN must be the diameter of the circle. So, okay, now, this is chord CN, that is the diameter of this circle according to rule 5. In the next step, we implement the converse rule of rule 5 on this peripheral angle CMN. So repeat quickly on rule 7, repeat again. Rule 5, rule 7 is the converse rule of rule 5. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees in size. In the drawing, we have a circle. This is peripheral angle ACB. We know that peripheral angle ACB subtend on AB, that is the diameter of this circle. And therefore, according to this rule 7, peripheral angle ACB that subtend on the diameter of the circle must be equal to 90 degrees in its size. So according to this rule 7, any peripheral angle that subtend on the diameter of the circle must be equal to 90 degrees in size. So we can actually implement rule 7 in our drawing. In our drawing, this is peripheral angle CMN. This is peripheral angle CMN that subtend on chord CN, that is the diameter of the circle. And according to rule 7, peripheral angle CMN must be equal to 90 degrees in size. Why? Because it subtend on the diameter of this circle, that is CN. So peripheral angle CMN equals to 90 degrees in its side according to rule 7. Those two angles are defined as vertex angles, and you know that vertex angles are equal to each other. But this angle equals to 45 degrees, and therefore this angle must be also equal to 45 degrees in its side according to the rules dimensions. Vertex angles are equal to each other. So in this small triangle EMN, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this third angle must be equal to 45 degrees in its size, according to the rule that says that the sum of the angles in any triangle, is equal to 180 degrees. Therefore, this first bisector must equal to 45 degrees in its size. What is the radius of this circle? The radius of the circle is defined as a line segment that starts from the center of the circle and that's on a point on the circle itself. Therefore, OB is the radius of this circle. What is the length of OB? According to what is given in the question, OB in total equals to OE, that is 5, plus EB, that is 4. 5 plus 4 is 9. So we found out that the radius of this circle equals to 9 units in its length. So write it down. The radius of this circle is equal to 9 units in its length. OA is the radius of this circle, therefore it is equal to 9 units in its length. Likewise, CO is also the radius of this circle, therefore it is equal to 9 units in its length. And finally, ON is also the radius of this circle, and therefore it is equal to 9 units in its length. Above all the radii of the circle are all equal to 9 units in their lengths. In the next step, we'll find out the area of this green triangle, triangle COE. Repeat again, we'll find out the area of this green triangle, triangle COE. What is the area of this green triangle COE? We know that the area of any triangle equals to the base of the triangle times the height to the base over 2. And therefore, the area of this green triangle CEO or COE equals to the base. We choose the base as CO. Times the height to the base. We know that the height to the base must rest 90 degrees with the base, or the height to the base must rest 90 degrees with the extended base. The extended base CO is CN. Again, the extended base CO is CN. So the height to the base of this triangle COE must rest 90 degrees with CN. So from point E, we draw perpendicular on CN. Again, from point E, we draw perpendicular on CN. So actually, this angle equals to 90 degrees in size. This angle also equals to 90 degrees in size according to our construction. We define the touching point of the perpendicular from point E and CN. This point is point G. So EG is perpendicular to CN. Again, EG is perpendicular to CN. Therefore, EG is the height to the base CN. Again, EG is the height to the extended base CO, that is CN. So we define EG as H. So the height to the base, the height to the extended base CO, that is CN, equals to H, because H creates 90 degrees with CN. Therefore, the height to the base, the height to the extended base is H, because it's creates 90 degrees with CN. So in total, we found out that the height of this triangle COE equals to H, because it's creates 90 degrees with the extended base CO, that is CN. The height is H over 2. So in total, we found out that the area of the green triangle COE equals to CO times H over 2. CO is the radius of this circle, that is equals to 9. So we substitute CO by 9 times H over 2. So in total, we actually found out that the area of the green triangle COE equals to 9H over 2 square units in its size. Likewise, we calculate the area of this lower triangle, triangle OEN. what is the area of this lower triangle, triangle OEN? The area of any triangle equals to the base of the triangle times the height to the base over 2. We choose the base of this triangle OEN, SON. The height to the base ON is h. Why? Because of the fact that h raised 90 degrees is the base ON. This angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. So the height to the base OE, the height to the base ON is h. So the height is h over 2. So in total we found out that the area of the lower triangle, triangle OEN equals to ON. ON is 9. 1 equals to 9. This is the radius of this circle. So we substitute ON by 9 times h over 2. So the area of the right triangle COE equals to the area of the right triangle OEN because of the fact that the areas of those two triangles are both equal to 9h over 2. Therefore, the area of the right triangle COE is equal to the area of the lower triangle, triangle OEN. In the next step, we calculate the area of this big triangle, triangle CEN. What is the area of this triangle CEN? The area of the big triangle CEN actually the area of the big triangle CEN must be equal to the sum of the areas of the two components that it consists of. The big triangle CEN consists of those two triangles, the green triangle and this lower triangle, triangle OEN. And therefore, the area of the big triangle CEN must be equal to the area of the green triangle. This is the area it is associated with the area of this green triangle COE. This is the first component that it consists of. Triangle COE, green triangle COE. Plus the area of the second component that the big triangle CEN consists of. The second component is this triangle OEN. So it is plus the area of this lower triangle, triangle OEN. But again, the area of the big triangle CN must be equal to the sum of the areas of the two components that it consists of. Triangle CN consists of those two triangles, the green triangle COE plus the lower triangle OEN. And therefore, the area of the big triangle CEN must be equal to the area of the green triangle COE plus the area of the lower triangle, triangle OEN. So the area of the big triangle CEN must be equal to the area of the green triangle COE, the small green triangle COE, plus the area of the lower triangle, triangle OEN. But we already found out that the area of the lower triangle OEN equals to the area of the green triangle COE. Therefore, we can substitute the area of the lower triangle OEN by the area of the green triangle COE because they are equal to each other on their sides. So the area of the green triangle OEN equals to the area of the green triangle COE. So in total, we found out that the area of the big triangle CEN is equal to the area of the green triangle COE plus the area of the green triangle COE. That is to say, it is equal to 2 times the area of the green small triangle COE. Here we divide this equation by 2, and finally we get that the area of the green triangle COE is equal to the area of the big triangle CEN over 2. That is to say, the area of the green triangle COE is equal to the half of the area of the big triangle CEN. You can say that the area of the big triangle CEN is twice as large as the area of the small green triangle COE. In the next step, we calculate the area of this big triangle CEN according to the rule that says that the area of any triangle equals to the base of the triangle times the height over 2. Repeat again. We will calculate the area of this big triangle CEN according to the rule that says that the area of any triangle equals to the base of the triangle times the height over 2. So the area of the big triangle CEN equal to the base of the triangle times the height over 2. Repeat again, the area of the big triangle CN equals to the base of the triangle times the height over 2. So the area of the big triangle CEN equals to the base of this big triangle CEN. The base of this big triangle CN. We choose the base of this big triangle CN as CE. The base is CE according to our choice. Times the height to the base. The height to the base CE must create an interest with the base CE. We can say also that the height to the extended base CE must create an interest with the extended base. The extended base CE is CM. Here, the extended base CE is CM. So the height to the base of this triangle CN must create an interest with the extended base CM. Here MN creates an interest with the extended base CM because of the fact that this is a right angle. So the height to the base is MN. divided by 2. This is a right triangle. This is also an isosceles triangle. Why? Because of the fact that those two angles, they are both equal to 45 degrees, and we have the rule that says that in front of equal angles in the triangle, they are equal size. So in the right triangle EMN, in front of those two equal angles, we have those two sides that must be equal to each other in their lengths. So if we define the length of side MN as B, then the length of side EM must be also equal to B units in its length because of the fact that they are equal to each other according to the rule that I mentioned. So in total, we found out that the height to the extended base C, that is CM, equals to B, because MN equals to B. MN equals to B, and CE equals to CQ, that is A, plus QA, plus QE, that is also A. So C in total equals to A plus A, that is 2A, times MN. MN equals to B units in itself according to our definition, divided by 2. So in total we found out that the area of the big triangle CEN equals to 2AB over 2. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. If I cancel 2, this expression equals to A times B. So in total we should found out that the area of the big triangle CN equals to A times B squared units in its size. The area of this big triangle CEN equals to A times B squared units in its size. We already found out that the area of the great triangle COE equals to the area of the big triangle CN over 2. And therefore, the area of the great triangle COE equals to the area of the big triangle CN. The area of the big triangle CN equals to AB. We have to divide it by 2. So in total, we found out that the area of the great small triangle COE equals to AB over 2 square units in its size. And again, the area of this great triangle COE equals to A times B over 2 square units in its size. In the next step, we will implement Rule 65 in our drawing. Repeat quickly on Rule 65. First of all, Rule 65 is true in any circle. This circle could be any circle. In any circle, if chord AB intersects with chord CD at point O, then the following equation is true. AO times OB equals to CO times OD. So, in the drawing of a circle, this is chord AB that intersects with chord CD at point O. Again, chord AB intersects with chord CD at point O. Therefore, in this drawing, the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So, we implement Rule 65 in our drawing. In our drawing, this is called AB. This is also the diameter of the circle, called AB. Intersects with chord CM at point E. Again, chord AB intersects with chord CM at point E. So all the requirements for Rule 65 are satisfied, and therefore we can implement here Rule 65. So, write it down. In our drawing, we have chord AB that intersects with chord CM at point E. Repeat again. Now we're going. Chord AB intersects with chord CM at point E. The intersection point between chord AB and chord CM occurs at point E. So all the requirements for Rule 65 are satisfied, and therefore we can implement in our drawing Rule 65. According to Rule 65, the following equation is 2. AE times AB equals to CE times EM. But again, according to Rule 65, the following equation is 2. AB times AE times EB equals to CM times EM. AE times EB equals to CE times EM. AE in total equals to AO, that is 9, this is the radius of the circle, plus OE, that is 5, according to what is given as the question. So AE in total equals to 9 plus 5, that is 14. So we substitute A in this equation by 14 times EB. EB equals to 4 units in itself, according to what is given as the question. So we substitute EB by 4. And it equals to CE. CE in total equals to CQ, that is A, plus QE, that is also A. So in total C equals to A plus A, that is 2A. C equals to 2A times EM. EM equals to units in itself, according to our definition. EM equals to B. So in total, we found out that according to Rule 65, 14 times 4 equals to 2AB. 14 times 4 is 56, equals to 2AB. Here we divide this equation by 2, and finally we get that AB equals to 56 over 2 is 28. AB equals to 28. But we already found out that the area of the big triangle CN equals to AB. The area of the big triangle CEN equals to A times B. But we just found out that A times B equals to 28. So we can write here that AB equals to 28. Oh, and from this equation, the area of the big triangle CN equals to AB equals to 28, we derive that the area of the big triangle CN equals to 28. The area of the big triangle CN is equal to 28 square units in its size. We already found out that the area of the green small triangle COE equals to AB over 2. So the area of the small triangle COE the area of the green small triangle COE equals to AB over 2 square units in size. So we just right now found out that AB equals to 28. So we substitute AB here by 28 over 2. 28 over 2 is 14. From this equation, we have that the area of the small triangle, the small green triangle COE equals to 14 square units in its size. The area of this small green triangle COE equals to 14 square units in its size. The next step, we calculate the area of this small green triangle COE according to the rule that says that the area of any triangle equals to the base of the triangle times the height over 2. So the area of the green triangle COE equals to the base of the triangle times the height to the base over 2. We'll choose the base of this green triangle COE as OE times the height. The height to the base must rest 90 degrees with the base, or we can say also that the height to the base must rest 90 degrees with the extended base OE. The extended base OE is EA. Again, the extended base EO is EA. So the height to the base must create 90 degrees with EA. CD creates 90 degrees with EA. Because this is right again. Again, CD creates 90 degrees with EA. So the height to the base is CD. So in total, we found out that the area of the triangle COE equals to the base OE times the height to the base CD over 2. OE equals to 5 units in itself according to what is given as the question. Again, the height to the base is CD. CD equals to X according to what is given as the question. X is the line segment that we are working for in this question. So CD equals to X, therefore we substitute CD in this equation by X divided by 2. So in total we found out that the area of the green small triangle COE equals to 5x over 2 square units in its size. But we already found out that the area of the green small triangle COE equals to 14 square units in its size. So we can write here that the area of the green small triangle COE equals to 14. And from this equation, 14 equals to the area of the triangle COE equals to 5x over 2. We know that 14 equals to 5x over 2. Those two sides of the equation are equal to each other. So we found out that 14 equals to 5x over 2. Here we multiply the equation by 2 and finally get that 14 times 2 is 28 equals to 5x. Here we divide the equation by 5 and finally get that x equals to 28 over 5. 28 over 5 is 5.6. So she found out that the length of this line segment CD is equal to x is equal to either 28 over 5 units in its length, or in terms of numbers, the length of line segment CD is equal to x is equal to 5.6 units in its length. But again, we found out that the length of line segment CD is equal to x is equal to either 28 over 5 units in its length, or in terms of numbers, the length of line CD is equal to x is equal to 5.6 units in its length. So we finish with the second question. In the next step, I will summarize the lecture. We start with the repetition of the solution of the first question, and then we repeat with the solution of this second question. The first question, our task was to find out the size of this angle APC is equals to x. So we have to find out the value of this angle, angle x. So in the domain we have triangle ABC. We know that BP equals to PC. So if we define the length of BPSA, then PC must also equal to A because they are equal to each other according to what is given in the question. In addition, we know that this is angle ABC is equal to 15 degrees in size. Likewise, this is angle ACB is equal to 30 degrees in size. Again, our task was to find out the size of this angle APC is equal to x. So we have to find out the value of this angle, angle x. First of all, BP equals to PC, so if we divide the length of BPSA, then PC must also equal to A because they are equal to each other. In the next step, we extended side ACA of this triangle ABC by a side line, and then we created angle of 15 degrees at point B in such a way that BA is one leg of this angle, and the other leg has 50 degrees if the leg AB. So this angle equals to 15 degrees in size according to our construction. In the next step, we extended this leg by a side line until it touches the extended side CA. And you find the touching point of the extended side CA with this extended leg. This point is point M. By doing this construction, we created the associated triangle, triangle BMC. Why triangle BMC is an associated triangle? Because of the fact that those angles are equal to each other, their sizes. Each angle equals to 30 degrees in size, and therefore they are equal to each other. BC is the base of this associated triangle, triangle BMC. And again, BMC is an associated triangle, and BC is the base of this associated triangle, triangle BMC. So here we can implement in rule 20 in our drawing. Please click on rule 20. According to rule 20, the perpendicular to the base of an associated triangle bisect the base. In the drawing, we have the associated triangle, triangle ABC. Triangle ABC is an associated triangle because AB equals to AC. BC is the base of this associated triangle, triangle ABC. According to this rule 20, the perpendicular AD to the base BC bisect the base BC. This is to say the perpendicular AD divides the base BC into two halves. The first half is BD, and it is of course equal to the second half DC. And each half equals to BC over 2 because of the fact that BC has been bisected. So DB equals to BD equals to DC equals to BC over 2. So here we can implement rule 20 in our drawing. Because we have the associated triangle, triangle BMC. BC is the base of this associated triangle, triangle BMC. According to rule 20, the perpendicular from point M to the base BC bisects the base BC. That is to say, it divides the base BC into two halves. Therefore, the perpendicular from point M to the base BC must touch the base BC at point P and not in any other point. Why? Because at point P, base BC has been bisected into two halves. The first half is BC is equal to A, and the second half is PC is equal to A. So in conclusion, we found out that the perpendicular from point A to the base BC must touch the base BC at point P. Because at point P, the base BC has been bisected into two halves. So this angle equals to 90 degrees, and this angle also equals to 90 degrees inside, according to our construction. So, in the next step, we focus on this right triangle BMP. The right triangle BMP, sin 40 degrees equals to MB, MP over MB. Again, this right triangle BMP, sin 40 degrees equals to MP over MB. So again, the right triangle BMP, sin 40 degrees equals to MP over MB. We find the length of the opponent MB as 2B. MB equals to 2B according to our definition. So in total, we found out that sin 30 degrees equals to MP over MB. MB is 2B, therefore MB by 2B. So in total, we found out that sin 30 degrees equals to MP over 2B. Sin 30 degrees is 1 half. So 1 half equals to MP over 2B. Here we multiplied this equation by 2B and finally found out that MP, the missing perpendicular MP equals to 2B over 2. We have 2 in the denominator, so 2 we can cancel. So in total, we actually found out that MP equals to B unit in its length. MP equals to B unit in its length. That is to say, we actually found out that if MB equals to 2B, then MP must be equal to B. In the next step, we'll focus on this big associated triangle BMC. This big associated triangle BMC. AB is the angle bisector of angle MBC of the associated triangle MBC. Again, AB is the angle bisector of angle MBC, this associated triangle MBC. Why? Because of the fact that AB bisects angle MBC into 2 halves. Each half equals to 15 degrees in size. And therefore, we can implement here angle bisector theorem. Angle bisector theorem is also defined as rule 19. According to rule 19, if you know that AD is the angle bisector of triangle ABC, that is to say AD bisects angle BAC into 2 halves. Each half equals to theta. So we know that AD is the angle bisector of angle BAC in triangle ABC. And therefore, angle bisector AD divides the sides of triangle ABC proportionally. That is to say, BD over DC equals to BA over CA. Again, because of the fact that AD is the angle bisector of triangle ABC, angle bisector AD divides the sides of triangle ABC proportionally. That is to say, BD over DC equals to BA over CA. So we can implement rule 19. It is also defined as angle bisector theorem on this associated triangle BMC. We know that AB is the angle bisector of angle MBC in the associated triangle MBC. I repeat again, AB is the angle bisector of angle MBC in the associated triangle MBC. So according to rule 19, angle bisector AB divides the size of this big triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. Repeat again, because of the fact that AB is the angle bisector of triangle MBC, angle bisector AB divides the size of triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. Repeat again. In the big associated triangle MBC, AB is the angle bisector of angle MBC, and AB is the angle bisector of the big angle MBC in this associated triangle MBC. And therefore, according to rule 19, that is also defined as angle bisector theorem, angle bisector AB divides the sides of triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. MB over BC equals to MA over AC. According to rule 19. MB is 2B, BC is A plus A, that is 2A, and is equals to MA over AC. Repeat again. MB is 2B, BC is 2A, and is equals to MA over AC. So in total, we found out that 2B over 2A equals to MA over AC. We have 2 in the denominator, so 2 gets cancelled. So in total, this side of the equation, we have left only with B over A equals to MA over AC. B over A equals to MA over AC. So in the next step, we focus on this right triangle MPC. This right triangle MPC, line 70 AP divides the sides of this right triangle MPC proportionally. That is to say A over B equals to MA over AC. Repeat again, in the right triangle MPC, line segment AP divides the size of triangle MPC proportionally. That is to say B over A equals to MA over AC. We already found out that B over A equals to MA over AC. And because of the fact that angle bisector AP divides the size of triangle MPC proportionally, angle bisector because of the fact that line segment AP divides the size of the right triangle MPC proportionally, line segment AP must be the angle bisector of triangle MPC, according to rule 21. So repeat quickly on rule 21. According to rule 21, this is line segment AD. We don't know that line segment AD is the angle bisector, but we know that line segment AD divides the size of this triangle ABC proportionally. That is to say, we know that BD over DC equals to AB over AC. So it is given us that BD over DC equals to AB over AC. That is to say, line segment AD divides the size of this triangle ABC proportionally. Why? Because of the fact that BD over DC equals to BA over CA. And therefore, line segment AD must be the angle bisector of this triangle ABC. Therefore, line segment AD is the angle bisector of triangle ABC. That is to say, line segment AD divides the angle BAC into two halves. Each half equals to theta. So here, because of the fact that in the right triangle MPC, line segment AP divides the size of this right triangle MPC proportionally, we know that B over A equals to MA over AC. Line segment AP must be the angle bisector of this triangle MPC. Line segment AP is the angle bisector of triangle ABC. That is to say, line segment AP divides angle MPC into two halves. Because of the fact that line segment AP is the angle bisector of angle MPC in this triangle MPC. So angle bisector AP divides angle MPC into two halves. Angle MPC is a right angle, so each half equals to 45 degrees in its size. This is the first half that is equals to 45 degrees in this size, and this is the second half. This is also equals to 45 degrees in its size. So in total, we found out that angle APC is equal to x is equal to 45 degrees in its size. So the answer to the question is that the angle that we are looking for in this question, that is angle APC, is equal to x, so angle x equals to 45 degrees in its size. So we finish to repeat on the first solution of the first question. In the next step, we repeat on the solution of the second question. In the second question, our task was to find out the length of this line segment CD is equals to x. Or we can say that we have to find out the length of line segment x is equals to CD. So in the drawing, we have a semicircle. Point O is the center of this semicircle. Those two angles are both right angles. We also know that PQ equals to CQ equals to DE. So if we find the length of PQ is A, then CQ and QE must be also equal to A because they are equal to each other and their lengths according to what is given us the question. In addition, we know that the length of line segment OE equals to 5 units. This is line segment AEB, this is equals to 4 units in its length. This letter is letter B. Line segment AB equals to 4 units in its length. Again, our test is to find out the length of line segment CD is equals to X, so we have to find out the length of line segment X is equals to CD. But again, because of the fact that PQ equals to CQ equals to QE, if we define the length of PQ as said, then CQ and QE must be also equal to A because they are equal to each other according to what is given as the equation. CQ equals to PQ equals to QE equals to A. In the next step, we join points P and C together by straight line. By joining points P and C, we get the triangle PCQ. We have the rule that says that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides in the triangle CPQ, we have those two angles that must be also equal to each other and their sizes. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha according to the rule that I mentioned. The sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in the triangle CPQ must be equal to 180 degrees. So alpha plus 90 degrees equals to 180 degrees. In the triangle CPQ, the sum of the angles must be equal to 180 degrees. That is to say, alpha plus alpha is 2 alpha plus 90 degrees equals to 180 degrees. If we subtract the 90 degrees from this equation, we found out that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. If we divided this equation by 2, we found out that the missing angle alpha equals to 90 degrees over 2, that is 45 degrees. Those two angles are both equal to alpha, and therefore each of them is equal to 45 degrees in size. So we actually found out that triangle CQP is a right triangle, and it is also an associated triangle. Why? Because CQ equals to PQ. So we can say in general that if we have a right triangle that is also an associated triangle, it always has three angles. The first angle will be equal to 90 degrees and the other two angles must be equal to 45 degrees in their sizes. This is true in any associated triangle, this is also a right triangle. In the next step, it is given as a equation that CE is a straight line. So if you focus on the upper side of the straight line CE at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles here we have at the right, at the straight line CE at point Q, we have this angle that is the right angle, plus this missing angle. In total the sum of those angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we join points P and E together by straight line. By joining points P and E, we get the right triangle PQE. In the right triangle PQE, in front of those two equal sides, we have those two angles are equal to each other in their sizes. So in total, we can say that the right triangle PQE is also an associated triangle, why? Because of the fact that PQ equals to QE. And we know that in any associated triangle that is also right angles, we have three angles. The first angle is equal to 90 degrees, and the other two angles must be equal to 45 degrees in their sizes, each of them. So those two angles equal to 45 degrees in their sizes. The next step, we completed this semicircle to a circle. Then we extended side PE by straight line until it touches the circle. We define the touching point of the extended side PE with this circle. This point is point N. Likewise, we extended side QE by straight line until it touches the circle. We define the touching point of the extended side QE with this circle. This point is point M. In the next step, we join points M and N together by straight line, and we join points C and N together by straight line. This is peripherical CPN. Peripherical CPN equals to 45 degrees plus 45 degrees is 90 degrees. Peripherical CPN equals to 90 degrees in size, and it's subtend on chord Cn. Again, peripherical CPN subtend on this chord Cn. So here we can implement rule 5. Repeat quickly on rule 5. according to rule 5, any peripheral angle that is equal to 90 degrees inside must subtend on the diameter of the circle. In the drawing, we have a circle. This is peripheral angle MAN. We know that peripheral angle MAN equals to 90 degrees in size. Therefore, according to this rule 5, peripheral angle MAN is equal to 90 degrees in size must subtend on the diameter of the circle. Peripheral angle MAN subtend on chord MN, and therefore chord MN must be the diameter of the circle according to this rule 5. So according to rule 5, any peripheral angle is equal to 90 degrees in size, like this angle. Any peripheral angle is equal to 90 degrees in size must subtend on the diameter of the circle. So we can implement rule 5 in our drawing. In our drawing, this is peripheral angle CPN. Is equal to 90 degrees in size. Therefore, peripheral angle CPN must subtend on the diameter of the circle. Peripheral angle CPN subtend on chord CN, and therefore, according to rule 5, chord CN must be the diameter of the circle. In the next step, we implemented the converse rule of rule 5, that is rule 7, in this peripheral angle CMN. Peripheral angle CMN subtend on CN, that is the diameter of this circle. Therefore, according to rule 7, peripheral angle CMN must be equal to 90 degrees in size. Repeat again, rule 7 is the converse rule of rule 5. Repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. This is peripheral angle ACN. We know that peripheral angle ACN subtends on the diameter of the circle. That is to say, peripheral angle ACN subtend on chord AB. We know that chord AB is the diameter of the circle. Therefore, according to this rule 7, peripheral angle ACN must be equal to 90 degrees in size. So according to rule 7, any peripheral angle subtend on the diameter of the circle must be equal to 90 degrees in size. So, in the drawing, we have peripheral angle CMN. That subtend on chord CN, that is the diameter of this circle, and therefore, according to rule 7, peripheral angle CMN must be equal to 90 degrees in its size. Those triangles are defined as vertex angles, and we know that vertex angles are equal to each other. But this angle equals to 45 degrees, and therefore, this angle must be also equal to 45 degrees in its size according to the rule that I mentioned. This small triangle EMN, small right triangle EMN, this angle equals to 45 degrees. This is the right angle, and therefore this angle must be equal to 45 degrees in size according to the rule that says that the sum of the angles in the triangle is equal to 180 degrees. In the next step, we calculated the area of this green triangle COE. What is the area of the green triangle COE? We know that the area of any triangle equals to the base times the height to the base over 2. But before that, what is the radius of this circle? The radius of this circle starts from the center of the circle and ends on a point on the circle itself. So the radius of this circle is OB. O is the center and B is the point on the circle itself. Therefore, this is the radius of the circle. OB in total equals to OE, that is 5, plus EB, that is 4. So in total, the radius of OB equals to 5 plus 4, that is 9. The radius of the circle equals to 9 units in its length. Likewise, OA is also the radius of the circle, that is 9. CO is also the radius of the circle, that is equals to 9. And finally, ON is also the radius of the circle, that is equals to 9. So in the next step, we calculated the area of this green triangle COE. The area of the green triangle COE equals to the base times the height over 2. We choose the base as CO, and the height to the base must get 90 degrees with the base or with the extended base. CO is the base, and the extended base CO is CN. The extended base CO is CN. So the height to the base must get 90 degrees with CN. Therefore, from point E, we draw perpendicular on CN. From point E, we draw perpendicular on CN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees in its size according to our construction. We define the touching point of the perpendicular from point E in CN. This point is point G. We define the length of line segment EG as H. H is the height to the extended base CO. H is the height to the extended base CO. The extended base CO is Cn. So H is the height to the base because it's greater than 90 degrees with the extended base Cn. This angle equals to 90 degrees and this angle also equals to 90 degrees inside according to our construction. So in total, I can find out that the height to the base CO is H. And therefore, in total, the area of the green triangle CON equals to the base, that is CO, times the height H over 2. CO is the radius of this area, that is equals to 9. The height is H over 2. CO equals to 9 times the height H over 2. So in total, we can find out that the area of the green triangle COE equals to 9H over 2. Likewise, we calculated the area of this lower triangle, triangle OEN. The area of the lower triangle OEN equals to the base of the triangle times the height to the base over 2. We choose the base of this triangle OEN as ON, and the height to the base must rest 90 degrees with the base. S rests 90 degrees with the base ON, because this is right angle, this is also right angle. So the height is ON, again the base is ON, the height is H over 2. So that we found out that the area of the lower triangle ON equals to the base is ON times the height is H over 2. So, but ON is the radius of this angle, that is equal to 9. So we substitute ON by 9 times H over 2. So in total we found out that the area of the lower triangle ON equals to 9H over 2 square units in size. But the area of the green triangle COE also equals to 9H over 2. Therefore, the area of the green triangle COE equals to the area of the lower triangle OEN. The big triangle CN consists of those two triangles. It consists of the green triangle COE plus the lower triangle OEN. And therefore, the area of the big triangle CN must be equal to the sum of the areas of the two components that it consists of. The first component is the green triangle COE, so it is the area of the green triangle COE plus the second component, that is triangle OEN. So it is plus the area of the lower triangle OEN. So in total, we actually found out that the area of the big triangle CN equals to the area of the green triangle COE plus the area of the lower triangle OEN, because of the fact that the area of the big triangle CN must be equal to the sum of the areas of those two components that it consists of. But we already found out that the area of the green triangle COE equals to the area of the lower triangle OEN. So again, we already found out that the area of the green triangle COE equals to the area of the lower triangle OEN. So we can substitute the area of triangle OEN by the area of triangle COE because they are equal to each other. So in total, we actually found out that the area of the big triangle CN equals to the area of the green triangle COE plus the area of the green triangle COE. That is to say, in total, the area of the big triangle CN equals to 2 times the area of the green triangle COE. Or the area of the green triangle CON is twice as large as the area of the green triangle COE. We divided this equation by 2 and finally found out that the area of the green triangle COE equals to half of the area of the big triangle CEN. In the next step, we calculated the area of this big triangle CEN according to the rule that the area of n triangle equals to the base of the triangle times the height over 2. So the area of the big triangle CN equals to the base of the triangle times the height to the base over 2. We choose the base of this big triangle CN as CE, and the height must create 90 degrees with the extended base CE. The extended base CE is CM. MN creates 90 degrees with CM. Therefore, MN is the height to the base. So the area of the big triangle CN equals to the base CE times the height to the extended base CE, that is MN over 2. In this right triangle EMN, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. So if we define the length of side EM as B, then MN must be also equal to B because they are equal to each other according to the rule that I mentioned. So we substitute the height MN by B. MN equals to B. CE, the base CE equals to A plus A, that is 2A. Again, in total we should find out that the base C equals to 2A and the height MN equals to B divided by 2. So in total we should find out that the area of the big triangle CN equals to 2AB over 2. We have 2 in the numerator and 2 in the denominator, so 2 we can cancel. So in total this expression equals to A times B. So in total we should find out that the area of the big triangle CN equals to A times B is current in size. Repeat again. The area of this big triangle CEN equals to A times B is current in size. We already found out that the area of the great triangle CE equals to the area of the big triangle CEN over 2. So the area of the great triangle CE equals to the area of the big triangle CEN. The area of the big triangle CEN equals to AB. So we substitute the area of the big triangle CN by AB over 2. AB over 2. So in total we found out that the area of this triangle COE equals to A times B over 2 squared in its size. So the area of the big triangle CN is twice as large of the area of this triangle CEO. The area of this triangle CEO equals to A times B over 2 squared in its size. The next step, we implemented rule 65 in our drawing. A bit quicker on rule 65. Rule 65 is true in any circle. This circle could be any circle. In any circle, if chord AB intersects with chord CD at point O, then the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule 65 in our drawing. Why? Because in our drawing, this is chord AB. It intersects with chord CM at point D. Again, chord AB intersects with chord CM at point D. So all the requirements of rule 65 are satisfied, and therefore we can implement here rule 65. Repeat again. Now we're drawing chord AB intersects with chord CM at point E. Point E is the intersection point of chord AB with chord CM. Therefore we can implement here rule 65. According to rule 65, the following equation is true. AE times AB equals to CM times equals to CE times EM. Again, AE times EB equals to CE times EM. According to rule 65, the following equation is to AE times EB equals to CE times EM. AE equals to 9 plus 5, that is 14. A equals to AO, that is 9, plus OE, that is 5. So in total, A equals to 9 plus 5, that is 14. A equals to 14 times EB. EB equals to 4 units in itself, according to what is given in the question. So we substitute EB by 4. And it equals to CE. CE equals to CQ, that is A, plus QE, that is A. So in total, C equals to A plus A, that is 2A. So we substitute CE by 2A times EM. EM equals to B according to our definition, so we substitute EM by B. Substitute EM by B. So in total, we should find out that 14 times 4 equals to 2AB. 14 times 4 is 56 equals to 2AB. Here we divided this equation by 2 and finally found out that AB equals to 28. AB equals to 28. We already found out that the area of the big triangle CN equals to A times B. But again, we already found out that the area of the big triangle CN equals to A times B. So we can write here that the area of the big triangle CN equals to A times B according to what we already found out. And we just found out that AB equals to 28. So we can write it that AB equals to 28, and from this equation, the area of the big triangle CN equals to AB equals to 28. We resolve that the area of the big triangle CN equals to 28 square in size. Those two sides of the equation are equal to each other. Likewise, we already found out that the area of the ring triangle COE equals to AB over 2. So we found out that the area of the ring triangle COE equals to AB over 2 square in size. AB is 28. So 28 over 2 is 14. So in total we found out that the area of this green triangle COE equals to 14 square units in its size. In the next step we calculated the area of this green triangle COE according to the equation that says that the area of green triangle equals to the base of the triangle times the height over 2. So the area of the green triangle COE equals to the base of the triangle times the height to the base over 2. We choose the base of this green triangle COE is OE, and the height to the base must create 90 degrees with the extended base or EO. The extended base EO is EA. So the height to the base must create 90 degrees with EA. CD definitely creates 90 degrees with AE because of the fact that this is a right angle. So the height to the base is CD, and the base is EO. So in total, we found out that the area of the green triangle COE equals to the base that is OE times the height that is CD over 2. According to what is given as the equation, OE equals to 5 and CD equals to X. X is the line segment that you're looking for in this question. So substitute OE by 5 and CD by X over 2. So in total, we found out that the area of the green triangle CEO equals to 5X over 2. But we already found out that the area of the green triangle CO equals to 14 square units in size. So we can write here that the area of the green triangle CO equals to 14 square units in size. And from this equation, 14 equals to the area of the green triangle CO equals to 5x over 2. We will derive that 14 equals to 5x over 2. Those two sides of the equation are equal to each other. So 14 equals to 5x over 2. Here we multiply this equation by 2 and finally found out that 5x equals to 14 times 2 is 28. So 5x equals to 28. Here we divided this equation by 5 and finally found out that x equals to 28 over 5. 28 over 5 is 5.6. So in total we actually found out that the length of line segment CD is equals to x. It is equals to either 28 over 5 units in itself, or in terms of numbers, the length of this line segment CD is equals to x is equal to 5.6 units in its length. Okay, thank you very much.